Hello, welcome back. The title of this lesson is called the Pythagorean Theorem. This is part 1. So the Pythagorean Theorem is honestly one of the most important equations or relationships in all of math, and I do mean that. Whatever grade level you're in, whether it's grade school or algebra or beyond, we always use the Pythagorean Theorem. I should say everything, lots of things are built on the Pythagorean Theorem, right? A lot of trigonometry that we learn with things down the road, sine and cosine and tangent, they're built on the Pythagorean theorem. A lot of calculus, and I'm actually going to share with you today some interesting things that we use the Pythagorean theorem for, even in the realm of like gravity theory and things like that. So things you wouldn't think it's applicable to actually are really integral in understanding modern theories of science. So I didn't realize when I first learned this thing how important it was. So I'm trying to front load that and let you know that this is critically important stuff used forever as you go on and learn. But we have to crawl before we walk, so we want to talk about what is this Pythagorean theorem. We'll do several problems, and after the first problem, I'm going to start to front load some of these applications and show you why it's very used in modern science and math and engineering. All right, so it all boils down to this thing called a right triangle. So I'm going to draw a right triangle on the board. My triangle is not perfect, but it's pretty good. Here is a right angle here. This means this is a 90-degree angle. And so the Pythagorean theorem, first of all, you have to know that the Pythagorean theorem, it only applies to right triangles. And a right triangle is a triangle that has one 90-degree angle. So this is called the Pythagorean theorem. I'll put TH for theorem. Theorem is just a mathematical rule that we know to be true, and it can be proven. So we're not going to prove this right now, but we know that it's true because you can go and build triangles and you can measure them, and we know the Pythagorean theorem holds, okay? So here is a flat board that we have drawn the triangle in, and we're going to show or do problems and show that the Pythagorean theorem is true on this chalkboard here, on this marker board. But I'm going to give you a clue. In a minute, after the first problem we work, I'm going to talk to you about what happens if you're not talking about a flat board. What happens if the space that you're dealing with is not a flat board, but a curved board, like a sphere? Or in the case of gravity theory, bent space, right? Because that's what modern theories of gravity are built around, is geometrical ideas of bending space and time, right? So we actually use the Pythagorean theorem or variations of it in very advanced theories to measure the curvature of space and time. I know it sounds crazy, but it all starts with a simple triangle here on the board. All right? So what we're going to do is label one of these sides A and one of these sides B. Now, it doesn't matter which one is A and which one is B. You could flip it around if you wish. But the longest side of the triangle, which is always the side opposite of the 90-degree angle, we always call that one C. So A, B, and C. Now, what the Pythagorean theorem says is that A squared plus B squared is equal to C squared. Now, what this means is if you build a triangle and you know that this is a 90-degree angle, remember it has to be a 90-degree angle, and you measure the length of A, and you measure the length of B, and you put it in here, and you take A times A, which means A squared. Whatever the length of B is, you put B times B, that's B squared. This addition here has to be equal to the third side C squared. A squared plus B squared is C squared, okay? Now I'm going to, again, front load a lot of ideas to you here. We're going to work problems, but I just want to caution you that this Pythagorean theorem works in everyday life here on Earth, on flat boards and such, but it does not work if your triangle is bent, like on a sphere or around a black hole, or something where gravity is bending and warping space and time. This Pythagorean theorem doesn't hold anymore because of the fact that space and time, we know gravity, or the modern theories of gravity talk about gravity being a byproduct of space and time being bent. So you have to kind of wrap your brain around that. I know I'm kind of giving you some advanced ideas for kind of an introductory lesson, but I really feel strongly that people know when they learn these things, like, hey, this isn't just applicable to triangles. Like, who cares about a triangle? This is applicable to how we learn how gravity works, how we learn how more advanced things work as well in calculus and in trigonometry. So what we're going to do for our first problem is I'm going to give you a right triangle. So I'm going to say we have a right triangle, and I'm going to tell you if A, the distance A is equal to 3, like 3 centimeters or something, and B is equal to 4 centimeters, then what will the hypotenuse C equal. Remember, the hypotenuse C is always the longest side. So it's like A is equal to 3, B is equal to 4, which I guess I have it backwards because 3 and 4 here. So you know what, just to make it a little easier, let's go ahead and erase that, and let's change it and make this B and let's A. It doesn't really matter, but you can see A is 3, and that's shorter than B, which is 4, so I flipped it around. If these two lengths of the sides are these, what would be the length of this? All right, so here we have to use the rules of algebra that we know. We know that A squared plus B squared always equals C squared for a triangle on a flat board like this, right? So let's put this information in. A is 3, so it goes in here, 3 squared. B is 4, which goes here. And we're saying that's equal to C squared. So let's just kind of hang on to this. We can't do anything with C yet, but we know on the left, from order of operations, we always do the squaring first before the addition. So 3 times 3 is 9. And we do the 4 times 4, which is 16. And we're saying that's got to be equal to C squared. Now, let me flip it around, because we can always flip it around and on either side of the equal sign. We can say that C squared is equal to, when you add these guys, 25. So here we have an equation. C squared is equal to 25. And we solved equations like that before. When we have a square, in this case we have C squared, we know that C squared, C times C, is equal to 25. So we want to undo the square. We have to get the variable C by itself. Remember, when you solve an equation, you can do whatever you want as long as you do it to both sides. I can add to both sides. I can subtract from both sides. I can multiply and divide from both sides. If I want, I can take a square root of both sides. And that's exactly what I'm going to do, because I know that I have a C squared, and if I take the square root of this, the square root and the squaring is going to go away. Remember, we learned that before, that the square is the opposite operation of the square root, and so it's going to go away there. So let's take the C squared here, and what we're going to do is we're going to take the square root of both sides. Now, anytime you solve an equation by applying your own radical like this, you always put a plus or minus somewhere on one side or the other. Again, we've already learned how to solve equations with radicals. So if you haven't done that, you need to maybe go refresh your memory on those lessons we've already done. But when you apply your own square root, we put a plus or minus, and that has to do with the way square roots are defined to begin with. All right? Now, remember, the square root operation cancels with the square, leaving only the variable C, which is what we wanted to do. Here we have the plus or minus, and the square root of 25, you know, is 5, because 5 times 5 is 25. Now, what this means is that this C can be equal to 5, or this C can be equal to negative 5. What we're saying is that the variable C mathematically could be two values, either 5 or negative 5. So let's put it in here. Here is the equation in the previous step. If I put 5 in here, 5 times 5 is 25, correct. If I put negative 5 in here, then negative 5 times negative 5 is also 25, check. So mathematically, there are two answers to this equation, because the variable C has a square on it. And when we have a square, we always have two answers. We learned that before also. So the problem, or it's not really a problem, it's just that in this case, we're talking about a triangle, and the length of the side C can either be 5 or negative 5. But even though the math tells you that there can be a negative 5 as an answer, we know that we're measuring the length of the side of a triangle. So we know that lengths can only really be positive. So what we do is we discard the negative 5 answer, and we basically say that the length of the side of this triangle has to be equal to 5. We can discard it because we know that in real life we cannot have negative lengths, right? Now you might say, well, why did the math lie to me? Well, math is math. It's a set of rules to give you answers. I'll give you another quick example. If this was a physics problem where we were talking about time, if we were to get a negative answer for time, you might think that's impossible too, but that's not really impossible. When you do an experiment, you start the clock. Tick, 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 the clock goes on. If I get a negative answer for time, like if I get negative 5 seconds, all it would mean would be that it's 5 seconds before the starting of my clock. So negative 5 seconds makes sense. It's just 5 seconds before I started my experiment. If I have a negative velocity, like negative 5 meters per second, if positive velocity is going down the road this way, negative velocity is just going the other way. It makes sense. But a negative length doesn't really make sense. So we know it's non-physical. We throw it away. And so the answer to this question is, If A equals 3 and B equals 4, then the third length of this triangle, the hypotenuse, has to be 5. Now notice that this is a special triangle, 3, 4, 5. I want you to remember that because it's one of the special triangles. The 3, 4, 5 triangle is always a right triangle. When you have one side is 3, the other side is 4, and the hypotenuse as 5, we know it's going to form a right triangle because it satisfies the Pythagorean theorem. So here we were calculating an unknown quantity. And the only way this triangle is a right triangle is if the third length is exactly what we calculated it to be, and then we know it's a right triangle because only right triangles, the Pythagorean theorem only applies to right triangles, right? Okay, now we're going to do a lot more problems, but before I go any farther, I want to talk a little bit more about this. Because when we learn things in math and in science, sometimes the things that seem so simple, you can actually extract a ton of learning out of very simple looking things. You know, Einstein was very famous for taking very simple thought experiments that most people wouldn't think twice about because they were so simple. And then he would take it to its logical conclusion, and then you get something crazy like, you know, time stretching, time dilation, or something like this. And you know, the students and the people that can look at a situation and extract as much out of it as you can are the ones that change the world. I'm not saying we're changing the world here. I'm just saying I want to talk about this a little bit more. Now, I want to discuss a squared plus b squared equals c squared one more time. All right? So what I'm going to do is draw this triangle down below. Something, maybe I'll do a little bit bigger, not too big though. A little bit smaller than before, but you get the idea. Okay, and this is a right angle, 90-degree angle. And we're saying that if this is side A and this is side B, then this is side C. Now think about what a squared means. A squared is A times A, right? So if you think of the length of the side of this triangle, if you think of it as forming a square with length side A, that's A, that's A, that's A, that's A. Then it's a square, right? Then what would A squared be? In fact, I think I'm going to put the A on the inside, right? What would A squared be? Well, A times A, that's the area of this little triangle over here. So when you look at the Pythagorean theorem, first time you learn it, you're like, okay, just use it. But now I'm trying to tell you, hey, it's a triangle, and when you look at A squared, it's just the area of some square attached to the side of the triangle there. And then you can do the same thing for the other sides. All right, you can say, all right, instead of just thinking of B like this, squared, I'm going to drag this guy down, and I'm going to make another square, and I'm not going to be able to make it exact because I'm not a human computer. But to get the idea that if this side is B, this side is B, and this side is B, let me take that and put it out here, like this, then what is B squared? It is the area of some square that has a side B on both sides all the way around attached to this part of the triangle. And I'm going to take this C and I'm going to move it on the inside, and then I'm going to draw, and I'm probably messed up because I'm not going to be able to get it to fit in there. You get the idea. Let me erase this and let me go up like this, something like this. Something like that. All right? Then this is C, and this is C, and this is C, and so on. So then we have the area of this third side. The area of a square, and this looks more rectangular. Sorry, it probably should go out a little farther. Something like this. So what we have here is C squared is equal to A squared plus B squared. It's the same thing. We just flip it around, right? So what have we done here? We've taken an equation which isn't really usually explained to students really any more than just saying, here it is, use it, okay? And then we turn it into something geometrical. We say that what this really is saying is that if you make a right triangle and you make a square off of one side and take the area of that square, and you make a square off the other side and make an area of that square, when you add these two surface areas together, it has to be equal to the area of the square that's attached to the other side. And just to make it a little more complete, it needs to probably come out more like this. But you get the idea, right? Something like this. So when I look at the Pythagorean theorem, you don't always have to do this, but you can try to think of it as an area relationship. In our universe, and I know it sounds mystical, okay? I'm not trying to be mystical, I'm just being real. in our universe, the rules of our universe are such that when you make a right triangle with a 90-degree angle like that, then the area attached to this side is a square, plus the area attached to this side is a square. When you literally count up all the square millimeters in there and add them to all the square millimeters in here, it has to equal the area of the other side, the longer side, the square attached to that. So it turns into a relationship with areas. All right. So now that you think about the Pythagorean theorem, not just predicting the length of a side, but as a relationship between areas, what do you think is going to happen if you draw this triangle on a bent surface, like a bent sheet of paper? Or better yet, let me give you another example. Here is my little prop here, a sphere. Let's say that instead of drawing the triangle on a flat board like this, I draw a triangle on a curved surface, something that's the space itself is curved. This means when I put my pencil down and draw it, I cannot draw a line in the same way that I can on this board because it's curved. Even if I think I'm drawing it straight, I'm really curving it throughout another dimension, right? So I can draw a triangle on this thing. I can connect three lines and I can make a 90-degree angle inside one of them. What do you think is going to happen? Now that you know that the Pythagorean theorem is kind of an area relationship, if you bend the thing, then it makes sense a little bit more, I think, that the Pythagorean theorem would not hold on a triangle drawn on a sphere because the areas would all be bent, right? And so the relationship wouldn't hold anymore. So this is really profound, right? Because if you actually, Earth is a sphere, right? It's not a flat place, even though we think it's a flat place. If you draw a large enough triangle halfway around the planet and measure the distance and make a right triangle out of it and try to put it into this equation, it won't work because the triangle's bent. Right? If you draw one on this thing right here and measure the lengths of the sides and put it in there, it won't work. It won't quite equal. In other words, it will not be equal to c squared, the length of the third side squared. It'll be either bigger or smaller depending on how the object is bent. Okay? Now you might say, that's wonderful, but I don't plan to draw any triangles on spheres. Okay, great. You may not do that. But let me tell you a little story and we're going to solve the rest of our problems. About a person named Albert Einstein, who was just a titan in understanding and writing theories of modern science. And I know that you know who this is, right? Well, his theory of gravity is a geometric theory. So, before Einstein, people thought that the force of gravity was just like a force that acted between two objects. But Einstein reformulated the idea of gravity as being a warping or a disturbance of space around a planet or a star. But not just space, a warping and a bending of time. And what I know that's hard to wrap your brain around, but time ticks, right? Like this. But around a black hole, it doesn't tick like that. It's bent. It's different than the time that would be ticking on a clock outside of a black hole, right? Space would be bent, time would be bent. And so, if we want to characterize the gravity around a black hole, we want to know how curved space and time is around the black hole. And the actual way that we do that is using a much more fancy version of this Pythagorean theorem. It's a little more complex than that, but that's the basic idea. What we call it doesn't matter so much, but there's an equation that you can then calculate based on the mass of the black hole or the star or whatever, how much curvature of space and time you're going to get. And the way that you calculate that is to see how different the Pythagorean theorem looks around a black hole than it does on flat space. That we have here on the board here. So around a black hole, it's not going to be equal. It's going to be either bigger or smaller than this. And how different it is, or how much bigger or smaller it is than this equation tells you how much more curved the space is. If the space and time is curved very, very extreme, then this thing will not hold at all. It'll be so different that it won't even equal at all. So then you might say, okay, but we're standing on a planet that obviously has gravity. So does this thing hold here? Well, the answer is not really. It's just that our planet doesn't have that much gravity. So any triangle you draw and you put it in here and you cut it out and you measure it, it's going to look perfect because the gravity around our planet is just not that strong. But if you go build a triangle around a black hole and do this experiment, then the deviation from this, in other words, you might put a squared plus b squared and you might predict 5, but it might turn out to be 17 when you actually measure c, the distance of the hypotenuse around a black hole. So that was a very large detour. And I know I threw this at you right after problem number 1, but I want to catch you before you go on to, before I lose you. So what I'd like you to do is, if that interests you, great, go research it further, but mostly just put it in the back of your mind and just realize that this stuff with triangles and Pythagorean theorem, it has modern uses that go beyond maybe what's explained in most classes. So I wanted to bring that up. All right, we're going to continue on with the rest of our problems. All right, let's move on to problem number 2. If I tell you that A, the length of one of these sides of a right triangle is 7, and B is equal to 5, and C is equal to 8, is this a right triangle? So whereas before I gave you only 2 sides and asked you to tell me the third one, in this case I'm actually giving you all 3 sides, and I'm just asking you, is this a right triangle? So what you have to do is just plug these values into the Pythagorean theorem and see if it's equal. And if it's equal, then it is a right triangle. If it's not equal, then it's either not a right triangle or you're in orbit around a black hole, in which case I told you the Pythagorean theorem doesn't work anyway. I know that we're not studying black holes here, but you get the idea. So let's do that. And don't forget, let's just just sketch one. We'll do it every little time here. You have, A and B and C. This is what we're talking about here. All right. So we know that A squared plus B squared has got to be equal to C squared. So let's put in some values. A is equal to 7, so that's 7 squared. B is equal to 5, that's 5 squared. And that's equal question mark. This is what we want to do, to see if it's equal to 8 squared. So A, B, and C. If it's equal, once we do this stuff, then we know it's a right triangle. And if it's not equal, then it's not a right triangle. All right, so 7 times 7, 49. 5 times 5, 25. And 8 times 8, 64. And when you add these guys together, you get 74. And this is not equal to 64. So because when we put these values into the Pythagorean theorem, there is no equal sign between the left and the right-hand side, not a right triangle. In other words, if you try to connect A and B and C with these links, you won't be able to close it. It won't form a nice closed shape if you try to do it. All right, now again, we're saying it's not a right triangle, but I'm also telling you that the Pythagorean theorem, it only really holds in flat space. So either it's not a right triangle, or your space is bent, or you're in a spaceship orbiting some black hole, in which case I already told you it's not going to equal anyway. So maybe that's what's happening. Who knows? But here we're going to say it's not a right triangle. All right. Let's take a look at the next problem. Here we have a right triangle with A equal to 12 and B is equal to 9. I'd like you to calculate what the value of C is, the hypotenuse. So the first thing we write down, A squared plus B squared has to equal C squared. A is 12, so we put 12 squared. B is 9, we put 9 squared, and that has to equal whatever C is. Now we know that 12 squared, 12 times 12 is 144, and we know that 9 times 9 here is 81, and we know that it has to equal C squared. So we'll flip it around and we'll say C squared is equal to the addition of this. So 144 plus 81 works out to be 225, and we want to get the variable by itself, right? So what we do is, since we have a square here, we do the opposite of that, which means we take the square root and we have to do it to both sides. And when we apply our own square root, we have to put a plus or minus to catch both of the answers, because we know from this equation, since it's a squared variable, we have to have 2 answers. We learned that before. So the square root cancels with the square, and what you're going to have left is the variable C, and you're going to have plus or minus. The square root of 225 works out to be 15. If you take 15 times 15, you're going to get 225. So what this means is that the variable C, the hypotenuse, can either be 15 meters or whatever it is, or C can be negative 15. However, we know we're talking about triangles. Triangles cannot have negative length, so we throw the solution away, we discard it, and we say that the hypotenuse, the length of the hypotenuse has to be 15. 15 meters or whatever units we're talking about. All right, cruising right along, let's take a look at problem number 4. All right, I'm going to tell you the sides of a triangle. A is equal to 6, and B is equal to 8, and C is equal to 10. Is it a right triangle? And this is a question, so you have to figure out the answer yes or no. So, again, we turn to the Pythagorean theorem. A squared plus B squared is equal to c squared. It's only true for right triangles. So A goes in, we put 6 squared in. B goes in, we put 8 in. And C, we're going to check and see if 10 squared is equal over here. 6 times 6 is 36. 8 times 8 is 64. And 10 times 10 is 100. And when you take 36 and 64, you get 100, which is indeed equal to 100. So what you say, yes, this is a right triangle, right? So these three sides can be fitted up to form a right triangle with a single 90-degree angle in there. That's what a right triangle is. All right, let's move along to, we have only 2 more problems left. Now this one I want you to pay extra attention to because it's a little trickier than usual. What if I tell you I have a right triangle with A is equal to 2, like meters or whatever, B is equal to 4 meters or whatever, and I want you to tell me what C is. Now you say, well, this is exactly the same kind of problem. Well, sort of. We'll get to it. Let's say that we put this into A squared plus B squared. Is it equal to C squared? We should say, is it equal to? We'll set it equal to C squared, and we'll calculate what C is. So A is 2, so 2 squared. B is 4, 4 squared. And then C squared is what we seek to calculate. So 2 times 2 is 4, and 4 times 4 is 16. And let's flip it around. Let's put the C squared over here, and 4 plus 16 is 20. So we have exactly the same sort of situation. We have a C squared. We want to get rid of the square, so we take the square root of both sides. And since we applied our own radical, we have to add our own little plus and minus to catch both answers. And then what we see is that the square root and the square actually cancel. So we're left with C is equal to plus or minus the square root of 20. And you're kind of stuck for a minute because you're like, what is the square root of 20? I don't remember what that is. You know, I know the square root of 25 is 5. I know the square root of 36 is 6. I know it's got to be in there somewhere, but I don't know what it is because I'm not a calculator. So, first of all, you can dump it in a calculator and get a decimal answer. That's fine, but we're going to use the skills that we've learned in the past. We're going to take this 20 and we're going to break it down into a factor tree to figure out the radical equivalent, the square root of this. 20, you can write it as 4 times 5, and 4 you can write as 2 times 2. And since you're looking for the square root of 20, that's what we're trying to do here, you're looking for pairs. There's a pair of 2s. I don't have any other pairs. So what you get here is that it has to be plus or minus the single 2 comes out of the radical, and the square root of 5 remains behind. If you don't know what I did there, then you just haven't watched my lessons on square roots. You have to know how to handle square roots in order to deal with the Pythagorean theorem because you always have square roots in there. If you're not sure what I'm doing here, go back to my lessons on square roots. We're just breaking it down into a factor tree, looking for pairs. Every pair of numbers you see, you pull them out of the radical, and everything else left behind stays under the radical. Now, because we can't have negative length, same as before, we just say that it's a positive 2 times the square root of 5. Now, this is the exact answer because you know all of these radicals, like square root of 5, they're all irrational, which means the decimals go on and on forever. They never really end. You can't really round them. Well, you can, but you're going to lose accuracy. All of these radicals are irrational like that. So this is actually the exact answer, 2 times whatever the square root of 5 turns out to be. But if you were to go to a calculator, and if you were to say, okay, I'm trying to find the square root of 20. If I go to the calculator and get the square root of 20, I'm going to get 4.47. Now, again, the decimals are going to go on forever. I'm rounding it there like this. And then if I instead calculate 2 times the square root of 5, then what I'll get is 2 times. If I take the square root of 5 into a calculator, I'm going to get, again, 2.24, which I'm rounding some decimal places. And then when I multiply this times 2 with enough decimal places, I'm going to see that that's basically the same thing as 4.47. I'm just showing you that when you get down to the answer, a lot of students are like, I don't understand this. What does this mean? All it means is if you take the square root of 5, you get a decimal times 2. That's the decimal answer. And you get exactly the same thing as if you just take the square root of 20 in the calculator anyway. This is a simpler way of writing the square root of 20 in the simplest form. If you want to circle the decimal approximation, you can. 4.47 is going to be the length of that side of that triangle. So if you have a triangle, length 2, and the other side is length 4, then the hypotenuse, if it's a right triangle, is going to be about 4.47. Now, that's not exact. You carry more decimal places to make it more and more exact, because the actual answer is 2 times the square root of 5, which is decimals that go on forever when you try to calculate it. All right? So we're using skills that we've learned before on how to simplify square roots, which is what we did right here. All right, this is our very last problem. After this, we're done. All right, let me ask you, if A is equal to 11 and B is equal to 6 and C is equal to 13, can this form a right triangle? Yes or no? So if it's a right triangle, it has to obey the Pythagorean theorem. A squared plus B squared is equal to C squared. So I put the 11 in here. I put the 6 in here. Question mark, is it equal to 13 squared? Now 11 times 11 is 121. 6 times 6 is 36. And 13 times 13 is 169. And when I add these guys together, I actually get 157, and that's definitely not equal to 169. And because the left-hand side and the right-hand side they're not equal, this cannot be a right triangle. The Pythagorean theorem has to be true for any right triangle, right? Since there's no equality here, this is not a right triangle. It doesn't mean I can't make a triangle with these sides. Of course I can, but if I try to make the triangle with those sides, it's not going to be a right triangle. There will not be a 90-degree angle. You'll probably have to bend it together a little bit too much, and that interior 90-degree angle will not be 90 degrees anymore. So in this lesson, we've covered a lot, and I took a gigantic detour in the beginning to teach you something that I'm pretty passionate about. I wish that when I was younger, the teachers would take a moment to tell me why I'm doing, or why I should care about what I'm doing. Because I could very easily have just said, hey, it's Pythagorean theorem, use it. And we would have just done the problems. We would have been like, okay, it's good for triangles. But you wouldn't know, like, what's that for? Right? Well, I'll just tell you and reiterate again. It's for a lot of things, but the entire branch of what we call trigonometry is based on right triangles. They're extremely useful for calculating things that are beyond the scope of this lesson, called sine and cosine, which we use, and that's how we describe waves, for instance. So even something weird like waves in the ocean, waves in space, they kind of rely on the Pythagorean theorem when you boil it down, because the way we write those equations have this at its base, as its foundational layer, right? I know it sounds weird, but it is true, right? Then when we move beyond that into modern theories of science, I taught you that, and we know that Einstein's theory of gravity may not be totally correct, but that's our best theory of gravity that we have right now, and it's a geometrical theory. And the way that we measure how curved space and time is to, the equations are a little different and the wording is a little bit different, but basically we formulate a type of Pythagorean theorem to measure the distance throughout space and time. And then we see how different is that distance than what we would predict in flat space with this, because the Pythagorean theorem holds exactly in flat space on a flat board with no gravity. But as soon as you have gravity, space and time are warped, even if you don't think they are. And the stronger the gravitational field, the more and more warped space and time is, to the point where if you tried to build a triangle around a black hole, you wouldn't perceive it necessarily, but everything would be so bent that the triangle, if you measure the sides, would not obey the Pythagorean theorem. It would not be exactly equal. And the more different it would be from equality, from what you calculate, like here, we got 3, 4, and we expect 5 for the hypotenuse. But around a black hole, you might not measure 5. You might measure like 37, because everything is bent so much that that's the case. And it boils down to, when you learn geometry later, you know that when you draw any triangle, the angles that are inside of a triangle add up to 180 degrees. Maybe you don't know that yet. Maybe you haven't learned it yet, but here's a spoiler. When you learn more about triangles, the angles, the 3 angles in a triangle, always add to 180, always, no matter what the triangle looks like. Except if you bend that triangle, for instance, I lost my little globe, by drawing a triangle on a globe, a bent surface. You try to draw a triangle on a globe, measure those angles, they're not going to add up to 180 because the space is bent. And the same thing with gravity. Gravity bends space. So this Pythagorean theorem stuff, I'm just trying to infuse in you a little bit of excitement that the stuff you learn now, which seems so boring and useless, actually has fantastic uses that we use every single day. And by the way, if we did not have Einstein's theory of gravity, then your phone or your computer with your GPS and your location on Earth would not work at all, because those satellites that give your position on the planet Earth, they have to know about Einstein's theory of gravity. And if we didn't know that, those satellites wouldn't work at all. So it's very practical that we have to, understand these things. So boiling it all down, a squared plus b squared is c squared. You can think of it in terms of area of some square attached over here, plus some area here has to be area of the other side. Solve these problems yourself, make sure you're comfortable, and then follow me on to part 2. We'll continue to build your skills.